This conference will now be recorded.
Okay, let's start it now. If it's not too bad, if not 1 minute is cut off. Okay, so you remember I was considering tree-like networks. So let me draw a tree-like network, which is not necessarily regular. Okay, there are things like this. And maybe there are occasional loops, but we'll neglect them. And then I told you that there's a criterion to know whether this network has a giant component or not. In the language of physics, this is called a percolation cluster. And the idea was to map this problem onto a problem of population growth, onto the Galton-Watson model. And so I tried to convince you that in this model, in this framework, you need to know the probability of that the node has k links outgoing from that node. So this is called the degree distribution. And then I told you that actually what is important for these type of questions is not P of k, but Q of k, which I showed was given by k P of k divided by the expectation of k according to P. And the idea of Q of k was not what is the probability that a randomly chosen node has k neighbors, but what is the probability that knowing that I have chosen that node, following a link from another node, what is the probability that that chosen node has k neighbors? And I try to convince you, and of course this can be made rigorous through Bayes' argument, that you increase the probability for nodes with a large degree simply because these nodes have a large number of friends, so you're more likely to choose them. Anyway, I'm not going back to this, but in the end of this discussion, I told you that if you think of propagation along this network as a kind of population growth problem, then there's an R0, a reproduction rate of the process that's growing, I mean, by analogy, which tells you whether or not you will have a giant component. And this R0, we found that it was given by the average value of k squared. So maybe I should stick to my notation from the past lecture. And I know I will have to move my camera in a second. So this was given by, and I'm leaving a space for a reason, the expectation according to P of k squared divided by the expectation according to P of k minus 1. So let me move my camera. Okay. And of course, if R0 is less than 1, then we know that the population stops after a while, and this means that you're actually on a finite cluster in the network. Whereas if R0 is greater than 1, then the process goes on forever, and it means that you have started on the giant component or on the percolation cluster. And so the criterion was that this should be compared to 1. So if this inequality is obeyed, then there exists a giant cluster. Okay. Well, now I want to know whether this giant cluster is robust, is resilient, or if it's going to crumble to pieces as soon as I'm attacking it. So, you can think of this problem as the giant cluster needs to be destroyed, because if you're in a model where you're actually modeling contagion of a disease along a social network, then you don't want a giant component to exist, because if a giant component exists, it means that a finite fraction of the population will eventually get infected. But if you think of this network as, for example, an electric grid or the internet, I mean a physical network, then if you destroy the giant component, this can have dire consequences for the functioning of the electric network, for example. And so you want this network to be robust against the failure of a few of its nodes. Okay, so depending on the point of view, you might be interested either in the resilience of the giant component or on the fragility of the giant component. But of course, these are dual problems. Okay, so now what I'm interested in is imagine that through an attack of this network, which can be, a physical attack trying to disturb the internet network or the electric grid of a country, or through a vaccination campaign, I take down a few nodes. Okay, so for example, this node is deactivated, this one is deactivated, this one is deactivated, and I call phi the fraction of nodes that are down. Phi is the fraction of disactivated nodes. So again, you can really, this is obviously a very topical subject. You can deactivate these nodes through vaccination if you think of a disease, because you can think that this guy, if he's vaccinated, he's not going to be able to further transfer the illness from one neighbor to his other crowd of neighbors. Okay, so what is the R0 in the presence of phi? So if you want, I'm going to add a possible dependence on phi here. And if you think about what it means to destroy or to deactivate some nodes, it means that from a given node, you're actually reducing the number of children. You remember that I worked with analogy with the Galton-Watson process. And so, you're coming from this node. So this is the parent. And this guy has a number of children. And the question was, how many children on average this node has? And this was the reason for the -1 here, because the average number of connection is this ratio. And then you have to remove one because one of the link is actually taken already by the father-son relationship. Okay, this was last week's or 2 weeks ago's argument. So now I have to count the average number of children, knowing that a fraction phi of the nodes has been deactivated. And so the argument is simply to multiply this quantity here by 1 minus phi. Okay, this is the reduction of the average number of children per node. And so the generalized criterion to know whether you have a giant component or not in the presence of this attack is very simple. It's just this modified Mallory criterion. So modified Malloy-Reid, which again I've argued using a little bit of hand-waving argument and this analogy with Galton-Watson, but believe me, you can actually do much better than that. And through the same kind of calculation that would be needed to establish the Malloy-Reid criterion to start with, it's very simple to get this factor 1 minus phi on top of it. Okay, so that's the result. And in order to make it a little more visual, I'm going to take an example. And my example is going to be that I have a network which has a degree distribution which is an exact power law. So I'm assuming that I'm constructing a network such that P of k is equal to A divided by k to the 1 plus mu, not only for large k, but actually for all k integer. Okay, so this is my model. I have a P of k which is given by an exact parallel. And A here is just a normalization. So this is a 1 parameter model. The only parameter is mu. So I have a certain A of mu here, which is such that the sum over k of P of k is equal to 1. Okay? So from this P of k, I can compute as a function of mu R0, and therefore I can draw a phase diagram as a function of mu for what's going on in these types of models. So what I'm going to draw is as a function of this parameter mu. I'm first going to draw P infinity, and P infinity, if you remember, is the probability that the randomly chosen node belongs to the giant component. Prob that a node belongs to the giant component. So, you imagine that as mu increases, this distribution goes down very quickly, and therefore it's going to be more and more concentrated for small values of k, for large mu. And therefore, if it's weakly connected for large mu, you expect that there will not be any giant component in that case. As you decrease mu, you have more and more what I call hubs last time, so nodes that are connected to many, many other nodes, and therefore you expect in this case that a giant component appears. So as a function of mu, let me indicate two special values. Then there's a transition as a function of mu, which looks like this. Let me change color, or maybe this is okay. So above a value of mu, which is roughly equal to 2.5, then P infinity is 0. And then between this critical value of mu and mu equal 1, there's a curve that does like this. And then below mu equal 1, P infinity is equal to 1. Okay? So what you see is that there are three phases in this model, in this family of networks. One when there is no giant component. One when there is a giant component, but it only occupies a fraction below 1 of the nodes. So not all nodes belong to the giant component. And then finally, for mu less than 1, then the distribution is so broad that everybody has to belong to the giant component, except a finite number of nodes in the large n limit. Okay, now on the same graph, I want to show what happens if you start attacking this network with some fraction phi of this activated node. So what I'm going to draw is phi c, what I'm going to call phi c, which is the fraction of node beyond which there is no giant component anymore. So this R of phi is given by this formula. And what I'm going to draw is phi c, which is defined by R0 of phi c equal 1. So as you increase phi c, as you increase phi from this formula, you see that you reduce R0. So if you start from a phase when there is some giant component, then after a certain value of phi, which I call phi c, the giant component will be destroyed. So that's the meaning of phi c. And if you compute phi c from, again, the same formula, what you get is a curve that does like this. So phi c is in blue. So what it means is that, of course, if there's no giant component to start with, then phi c is 0. You don't need to destroy anything. The giant component is already not there. Then in this little region of the phase diagram between 2 and 2.5, then you need to apply some fraction phi c to destroy the giant component, but this phi c is less than 1 until you reach mu equal 2. And for mu equal 2, actually, if you want to get rid of the giant component, you need to remove a fraction of site, a fraction of node, which is equal to 1. So this means that in this whole region, the giant component is resilient. It's very resilient because you really need to vaccinate nearly 100% of the population to get rid of the transmission rate. So this is due to super spreaders. And of course, as again, it's a very topical subject. You know, if the distribution of if the social networks are such that distribution of degree is narrow enough, then ideas like collective immunities and things like that that are simply related to R0 are valid. And so, as you know, if in a naive model, the collective immunity, which is phi c essentially, is given by 1 minus 1 over R0. So that's in a naive model. And so if R0 is 3, which is, we believe, the natural reproduction rate of the COVID, then 1 minus 1 over 3 is 2/3. And it means that 2/3 of the population need to be immune for the epidemic to stop. So that's the number that we heard in the last year. It's pretty high. You know, 2/3 of the population need to have had COVID for a natural immunity to take place. But you see that if the social network contains super spreaders, then it's much worse than that. Then you need to go beyond this naive immunization rate to get immunity. Okay, so this looks depressing. However, if you know that the network is of that form, then there's a trick to increase the vaccination efficacy. And the trick is related to the argument that we use to get this result. Okay. So, you know, if, of course, you don't know the degree of people, you cannot know how many friends a given person has. So what you can do in order to improve a vaccination campaign is, so the first idea would be to vaccinate people randomly, but you can do a little better than that, and in some cases much better than that, by contacting someone at random, and then asking this person to name a friend who should be vaccinated. And if you do that, then you're exactly in the context of this selection process that I've described that transforms P of K into Q of K. And by this simple trick, actually, you can enhance tremendously a vaccination campaign and lower the density of phi that you need to reach to get rid of the giant component. And in a sense, it's intuitive. It's related to what I told you here. I told you that the P infinity is equal to 1 in this region because of the hubs. So if you target the hubs, then you're going to remove the giant component much more efficiently. And the idea of targeting the hubs is a little bit what's contained in here. If you don't know, of course, in an electrical grid, you can count it's sometimes public information, the topology of the network. So if you're a terrorist and want to destroy an electric grid, you know obviously that you should target heavily connected nodes, but this is easy to find. In a population, in order to detect who is connected to many people, is much harder. But this trick, this conditioning trick, makes part of the way. So I think it's an interesting, it's an extremely interesting example of this little paradox that your friends on average have more friends than you have, that you can turn to its head and use as a tool to improve the vaccination campaign. Okay, so this is the end of my chapter 3. And so now I can move to chapter 4, interactions and collective effects. So what I'm going to talk about is what I actually started my lectures with in the very first session. I told you about crises, discontinuities, and all these effects. And so what I want to show you is a simple model where you can understand that depending on some parameters, you can either have a slow evolution, smooth evolution, for example, the state of optimism of a population, or the bullishness of people to buy the stock market, or the trust in the banking system. Many examples like this. So in some cases, you can find that this optimism, say like this, is evolving in a gradual, smooth way. But in other cases, as we know, there seem to be tipping points beyond which there's a sudden breakdown of trust or of optimism. There are crashes in financial markets and things like that. And so we want to understand why in some cases things seem smooth and in other cases they seem abrupt. I think it's very striking to see that in many social contexts, you can have very sudden shifts in the way people perceive a problem. I guess that the last 20 years in terms of child abuse in France in particular, it's very striking to see how child abuse was tolerated even in the 90s, and now it's completely unacceptable. And so these kind of pretty rapid change of cultural norms in a society, I think, are extremely interesting to understand from a theoretical point of view. Okay, so what I'm going to present to you is what's called the random field Ising model. And it's, of course, a model that's been introduced in a physical context. So this is the physics of random magnets. And the model, in terms of describing the physics of random magnets, has had a lot of successes, in particular in describing what's called hysteresis loops. And I'll go back to that in a second. And so what I'm proposing here is to transpose the random field Ising model to cases where people have to make binary decisions. So I'm going to imagine that agent I, has to make a binary decision, which I'm going to call, of course, a spin. So Si at time t is equal to +1 or -1. And this binary decision, as I said, can be many things. It can be buy or sell the stock market. It can be vote right or vote left. It can be buying a cell phone. I'm speaking about this because there is data on how cell phones in the 90s invaded the market. So, of course, you're much too young to imagine a world without cell phones. But in the 90s, at first, it was not obvious at all that one should get a cell phone. So, imagine by cell phone, because as I said, there is data that I have analyzed myself on this problem, but you can imagine more generally buy a new technology. Tax evasion, you can also imagine that whether you should dodge taxes or pay your taxes. In some countries, it's been a sport for a long time to dodge taxes, but we can think of that as being part of the problem. In the US, there's the gun problem. Should you buy a gun if you live in the US, or should you be for gun control? All these binary examples you can have in mind, and you'll see why I'm putting all this in the same basket. So the rule of the random field Ising model that I want to transpose here, let me write it down, and then I'm going to comment what I'm trying to model. So Si at time t plus 1 is the sign of the sum of three terms. So it's a sign because this can only be plus or minus 1. So there's a term that I'm going to call capital H of t, which is common to everybody. You see that here there's no I. So that's what I'm going to call common information or public information. Then there's a term that's specific to each agent, which I'm going to call H little I. So this term here is I dependent, but it's T independent. It's static in time. So this is the random field in the Ising model. So this is an idiosyncratic preferences. Okay. So it means that, depending on who you are, depending on where you're born or what's your background and so on, you may be more inclined to vote left or to vote right, or to be for the right to hold guns or not, and so on. And then, of course, the crux of the model will be to introduce some social interaction. And so the social interaction I'm going to write as an interaction between spins, which is sum over j of jij sj of t. And in the context of what I'm going to speak about today, I'm going to imagine that all these jij's are positive or zero. So jij means that the network of the jij tells you who I is listening to in order to make his decision at the next time step. So the j is such that jij is non-zero are the neighbors influencing I. And then depending on what these neighbors are doing, then you tend to follow their advice, or you tend to imitate what they've done. Okay. And I'll show you later on a little funny video of illustrating how strongly we are influenced by what other people do. But I guess this is, if you do a little bit of introspection, you know that this is real, that what people around you are doing is very efficiently affecting your own decision. Anyway, so at this stage, this is the model. The model tells you that what you're deciding at the next time step is determined by a combination of three aspects. One is public information. So if I go back to my example of cell phone or technology, then public information is, for example, the price of cell phones. If the price of cell phones is very high, you're not very likely to buy the cell phone. So if you imagine that SI equal +1 means that you buy a cell phone, and H is very negative, then there's a chance that you will not buy a cell phone because of prices. It can also be because of the level of technology. So to go back to the 90s, in the 90s, cell phones were not working very well. There was a lot of interferences and network problems, and so it was not, we're not really excited by the idea necessarily of buying a cell phone. Then there's your own idiosyncratic preferences. So if you're a geek or if you're prone to buy new technology, there's a lot of people like this, then your HI will be large positive. If on the other hand, you're like my grandmother, say, then you will wait a long time before getting convinced or even never get a cell phone at all. So HI will be a random variable, but random not in the sense of time dependent, but random across the population. And it's going to be distributed according to some rho of H. And so this rho of H, I'm going to assume that it has a shape like this, Gaussian, for example, or unimodal. If it has more than one maximum, then what I'm going to tell you today needs to be a little bit amended, but I'm not going to use this today. So unimodal. And it's characterized by some width sigma. The mean is irrelevant because the mean I can always shift to 0. I'm going to assume that E of H is 0 because the mean of HI I can always put into capital H. Okay, if HI has a non-zero mean, I can subtract the mean and add it back to H of T, and it's going to be a kind of public information. So this is without loss of generality that I can impose that the mean of H is 0. And finally, the imitation term, the social pressure term, is characterized by some J's. And so J gives you another scale in the problem, if you want. Sigma is one scale, and these J's, so I'm going to assume that these Jij's are all of order J if they exist. Then you have two scales in the problem. One is sigma, and the other is J, and these two scales will give you a sense of whether heterogeneity of the population is dominant or whether social pressure is dominant. So we'll see that what matters is actually the ratio of these two scales, J over sigma. But intuitively, you can think that if sigma is very large, if people are very heterogeneous, then social pressure will play less of a role because people are stubborn in a sense, and that some H are very large, and these people, they never get influenced by others. Whereas if sigma is very small, so in the case of very homogeneous population, then the social pressure term will play a crucial role. So that's already at the level of just the thinking about the model, what we can imagine will happen. Okay, so now let me explain with a graph what's happening in this model, and then explain to you how one gets these results in the special case of a mean field model, where the Jij's again will be simple enough for the calculations to be completed. Okay, so I'm going to first, as I said, just draw a graph and then explain how you can actually compute what's going on. So what I'm going to assume is that as a function of time, h of t starts at minus infinity and ends at plus infinity. So if you look at this equation here, it means that whatever social pressure and idiosyncratic preferences, when h goes to infinity, these two terms are negligible, and therefore everybody takes the decision -1. Okay, so everybody is staying on the sidelines, if you want. And then as h increases, we expect that more and more people will get convinced to buy a cell phone or to vote left or right or to buy the stock market, whatever. And you expect that SI will progressively flip from -1 to +1. And when h goes to infinity, you expect that everybody's convinced. And so all the SIs are equal to 1. So in order to describe the system, I'm going to introduce what's in physics is called the magnetization of the system, which is just the average decision. So it's 1 over n, sum over I of SI. Okay? And of course, m depends on t because the SIs will depend on t. So what do you expect to find? So of course, m is between +1 and -1. And what I'm claiming is that depending on the ratio of j over sigma, so this is going to be the important parameter in the model, then you can have two different types of curves. I'm going to use 3 colors. I know that you don't see the red very well, but I guess that it's not going to be too difficult to see what I'm drawing. But tell me if really you don't see the red. So the first case, what I'm going to draw in blue is j over sigma equals 0. And in this case, what you're going to see is a perfectly continuous curve. So I'm drawing it like this. And if j equals 0, we're going to write an equation for that. But essentially, you're going to convince people one after the other. So for h very negative, in my example, in my geek example, the HIs that are very, very positive will be able to flip first. And then as you increase h, you're going to convince more and more people. And then at the end of the process, you'll convince the people who had the HIs very negative, so who were less prone to buy the new technology. And so this is going to be a continuous curve, which we'll see is going to be very simply related to the distribution of h. It's actually the cumulative distribution of h that you're seeing here. So if the distribution of h is smooth, then its cumulative is also smooth, and you get this type of curve. Okay. So this is a well-known problem in marketing, and people have studied this in the marketing area. Is how to describe this curve, how to model this curve. So this is usually called the early adopters. And this is the late adopters. And in general, this is an S-shaped curve that tells you how a given product, a given new product, is going to invade a market. But now if you increase j over sigma, so I'm going to draw in green the case where j over sigma is small, positive but small, then what you get is essentially the same kind of curve, except that it's going to be steeper. like this. And the intuition is that at the beginning, it's actually below the blue curve. So my drawing is not very good already. Sorry for that. It's below so look at this part. It's below the blue curve because of social pressure, which is not dominant, but it exists. Then because you see that other people are not buying, they're not convinced, you think, well, maybe it's not a good idea to buy now, and therefore you need better public information in order to be convinced. But then as people get more and more convinced, you see that there's a steepening of the curve, which means that the speed of adoption is increased compared to the case j equals 0. And then you flip from one state, -1, to the other state, +1, at a more rapid rate, okay? And again, thinking back about the 90s, I remember very well that in the 90s, at the beginning, not only the technology was pretty bad, but also prices were high, but also many people considered completely ridiculous to walk in the street with a cell phone or to speak in a cell phone in public and so on. So there was, a real social pressure that prevented cell phones to invade more rapidly the market. And then finally, if J over sigma is large, which means J over sigma larger than some critical value, which I'm going to call AC, and we'll see how this critical value is determined, then you get a completely different curve. And what you get is something that starts very low and stays very low because social pressure is so high that nobody actually flips. So if you think of, I don't know, the tax evasion, for example, you can think that the social pressure telling you, well, it's ridiculous to pay taxes, you shouldn't pay taxes, and so on, is so strong that people actually don't pay taxes until it becomes really costly to dodge taxes. So that will be H of T. H of T would be governmental measures to punish people who don't pay taxes in this case. And so the level is very low, and actually it stays low beyond the point, beyond the special point here, where the slope of the curve in the absence of interaction is maximum. So you see this point here is the point where the blue line has the maximum slope, is the point where the green line has a maximum slope, and you have to wait beyond the time that you would have waited in the absence of social pressure to see something. And what you see is first an acceleration of this line here, and then a sudden discontinuity. Let me try to draw it better. Like this. So this is a discontinuity with a jump of size that I'm going to call delta. And you see here, really, there's something completely different that happens, which is that suddenly a finite fraction of the population flips more or less at the same time. Here, on the other hand, in the case when J is small, it's really individual flips that build this curve, this continuous curve in the large n limit. But if you zoom, you see that each time you see one or a few flips, whereas in this particular case, at one point, there is, in a sense, the same effect as I was talking about in the context of the Galton-Watson model, and you'll see that the analogy is real. There's an infinite size avalanche of people flipping together. So what it means here is that as more people flip, they're going to convince more people to flip. And so the question will be, if I flip, how many people do flip because of me? And as you can imagine, if the R0, if the propagation rate of this conviction mechanism is greater than 1, then some catastrophic events will happen. And this is exactly what's going on in this model, and that I'm going to show you in details in a few moments. Okay, so first, innovation compared to the case without imitation. Without imitation, curves are smooth. With strong enough imitation, there's a sudden discontinuity that happens. Now, the second thing that is interesting about this model is what happens on the way back. Okay, so imagine that, of course, in the case of cell phones, this is silly because the technology never goes back in time. But imagine that we're speaking about an economy or the stock market. Then you can think of this red curve as the number of people who are optimistic about the state of the economy. And so in the case where there's strong enough imitation, you're going to remain pessimistic because other people are pessimistic until a point where, okay, news are better, H of T has increased, but also social pressure is such that suddenly everybody's extremely optimistic and starts buying houses and spending and so on. And so you can have this boom phenomenon that sometimes happen in an economy. So, okay, so that was on the way in. So I'm going to add a little arrow here. So that's what happened on the way in. But then imagine that news gets bad again. For whatever reason, the objective news about the state of the economy degrades. And therefore, you're going to go back in reverse. So what happens in that case? Well, in that case, when H of T starts back from plus infinity and then decreases, it's not the case that you're going to follow the same curve backwards. Actually, you're going to follow the equivalent of the lower branch for a while. And then at this point here, you're going to jump to the second equilibrium. So there's a region here where what's called in physics a hysteresis loop, and which is a very interesting phenomenon. And this hysteresis loop happens because for the same value of H, there can be more than one equilibrium state. So if I take this value of H, for example, then you see that there are two possible equilibrium states that will emerge from the equations, and therefore which one you choose depends on history, for example. And if the history is such that you come from the lower branch, you will stick to the lower branch for a while before jumping to the second equilibrium. And if you come from the high equilibrium branch, you'll stick on the high equilibrium branch until you jump to the lower equilibrium branch. And these points here are exactly the points where instead of having two equilibrium, there's only one remaining. So at this point, you don't have a choice anymore. At this point, you had a choice, the choice being pessimistic or optimistic. But at this point, it's no longer an option. The only point in which you can be is the optimism state. And here again, below this value of H, the only equilibrium that survives is below the pessimistic state, if you want. So this is really interesting because it shows that in some cases, you jump, but it's not because the other equilibrium state did not exist before. It's just because you were stuck on the one that you started with, okay? So this is a very generic model for many things, but in particular for the appearance of discontinuities in the evolution when the evolution of public information is smooth. So you see, this is really the main message, is that in all the examples, I mean, implicitly here, I'm assuming that H of T increases progressively or decreases progressively. So public information is smooth and continuous. smooth, and continuous, or continuous and smooth if you prefer. But the reaction of the system, m equal 1 over n sum over I of Si, is discontinuous, can be discontinuous. And for me, this is one of the big paradox or the big mystery of social sciences or stock markets, is that indeed, in many cases, you see that public information is progressively unfolding, but the reaction of the market can be extremely violent. And I don't know how many of you are following what's going on in the stock markets or in the bond markets actually right now, but it may be a case where there are two equilibria behind what's going on, and we're on the verge of flipping from one to another. I don't know, of course, but there are reasons to believe that such a scenario might be at play as we speak. Okay, so let me now go to telling you a little bit how do we get these results. So what I'm going to show is how you solve this model in the mean field limit. But what's interesting is that the phenomenology that I've drawn for you is actually much more general. And even if you have a generic network model describing social pressure, then in a very large number of cases, for a very broad variety of networks, the phenomenology that I'm going to talk about is valid. I'm going to tell you at the end how some networks are different, but it's the mean field approximation is not inventing a phenomenology that doesn't exist in more realistic cases. It's a pretty faithful approximation. So what I'm going to assume is that Jij is equal to J0 over n for all pairs, which means again that everybody is connected to everybody else. And I'm going to give another interpretation that's a little more convincing in a second. But for now, you imagine that you take your cues from a very large number of people, and all of them have the same influence on you. So in that case, if I compute sum over J of Jij Sj of T, then if all Jij's are equal, this is equal to J0 over n sum over J of Sj of T. But from my definition, 1 over n sum over J of S of J of T is equal to M. So this is J0 times M of T. Okay. So here, of course, if I had to be pedantic, I should exclude I from the sum, or assume that Jii is 0. And so, of course, you could, quibble on the fact that there's a n minus 1 term here, which is not exactly equal to m. But what I'm going to say is, of course, always true in the large n limits. So I can neglect the difference between n minus 1 and n. Okay, so now what I can get is a very simple self-consistent relation that is going to tell me how m evolves, because if I sum this equation on both sides, so what I do here is I do 1 over n sum over I this, 1 over n sum over I. And what you get is that m of t plus 1 is equal to 1 over n, the sum over I, such that hi is greater than minus h of t minus j0 m of t of plus 1. So you see this sign here, it's equal to plus 1 if hi is sufficiently large compared to minus h minus j0 m of t, plus 1 over n, sum over I such that hi is less than minus h of t minus j0 m of t times minus 1. Okay? So in order to give this equation a better looking shape, I'm going to introduce a slightly different quantity, which I call phi, which will be useful, which is a probability, well, which is 1 over n sum over I of such that Si is equal to plus 1. So it's a fraction, not a probability, it's a fraction of spins equal to plus 1. And it's clearly related to m. So m is equal to 2 phi minus 1. So it's just a trivial transformation from m to phi. And then what you get is that phi is given by what I'm noting p larger than minus h minus j0 m, which is p minus h plus j0 minus 2j0 phi, where this quantity here is just a cumulative distribution function. So ph of x is the integral from x to infinity ph of rho of h. So rho of h again is the distribution of idiosyncratic preferences, and this is the cumulative or complementary cumulative distribution. So it's the probability that small h is larger than some quantity. And so you see that, oops, I forgot the times. You see that I can convert this equation here into this equation here. So what I'm actually computing is phi of t plus 1 is equal to p of, there's a t index everywhere. Okay, so the trick that helps you solving the model in the mean field case is that you can have m or phi appearing in both sides of the equation, which of course would not be the case if the JIJs were only local, because in this case, what would happen is that there are only local magnetization, local fields, and not the mean field that you can compute from the left-hand side by summing it over i's. So of course, this is a very special situation, but as I said, it's not going to be terribly different from a more realistic network. So why is that assumption not that irrealistic? Well, you see that what it means if you see this equation here, it means that social pressure is actually equal to or proportional to the fraction of people who have already adopted, or the fraction of people who think left or think right, or any other ways you want to picture the model. But this means that actually you're sensitive to polls, you're sensitive to surveys, because surveys are supposed to give you an indication of what the other people think. And so, in a sense, it's not such a ridiculous assumption to use this mean field approximation, because it means that what influences you is not your network of friends, but it's the opinion of the majority, or at least a proxy for that, which is given by, for example, surveys or polls that are published in newspapers. And in the case of stock markets, you can think of the price of the stock market, as a way to indicate how many people are optimistic or pessimistic. So the fact that the public information, so to say, is related to social pressure is not such a crazy idea after all. Okay, so I'm going to just erase these definitions and rewrite them to have a little more room. So I've introduced two notations that are related, M and phi, and I'm going to flip between them depending on the problem I'm discussing. But let me skip back to M. And so what I got was, in terms of M of t plus 1 is 2p, the 2 minus 1 coming from the relation between phi and M, minus h of t minus j m of t minus 1. So this is what dynamically sets the evolution of the average opinion. So let me try to see whether there are stationary solutions to this equation. So imagine h of t stops changing with time and is given a some value h. Is there a value of m such that this equation is stationary? So I'm looking for fixed points. I'm looking for possible solutions of the equation m star equals 2p larger than minus h, which I'm assuming to be static for a second, minus 1. So what are the solutions of that? And you see, this is really the question I need to answer to know whether I can have two possible points where I sit or only one. Okay, well then, as usual, you need to solve such an equation. And the way to solve this equation, or to get some intuition, is to make a drawing again. So as a function of m, let me plot the right-hand side. So again, m is between minus 1 and plus 1. So I have the diagonal, which is going to look like this. And then depending on the shape of p larger than, I can have curves that look like this, for example. So in this case, there would be only one solution. But I can also have cases where this looks like this. And in this case, I would have three solutions. And in the case where there are three solutions, actually you can look at the slope of these curves at the intersection point, and you quickly realize that when there are three solutions, only two of them are stable because they have slopes less than one, and one of them, this one, is unstable because it has a slope larger than one. And so in the case where there are three solutions to this equation, there will be only two solutions that are stable and one solution that is unstable. But in fact, this solution exists, this third solution exists. So if I had to be slightly more precise on this graph, I should actually add a dotted line that does like this, which is the location of the third solution. And although you cannot sit on this line, so it's not a line that really exists, it has some important, I mean, the existence and the location of this line has some important consequences in the case where you start the system with a random choice, with people in a random state, and for a given value of h. And then depending on where you start from, so if the initial point is this point, you're going to flow to this solution. And if the initial point is here, you're going to flow to that solution. So if instead of having an h that varies with time, I have an h that's fixed in time, but a population that starts randomly with a random fraction of people that are convinced, then depending on the position of the initial condition compared to the unstable solution, you go one way or the other. So in some cases, it's really important to know where this unstable solution lies. So of course, many of you will have recognized the story of the van der Waals liquid-gas transition, and it's actually very, very similar to the phenomenology, except that here we're formally at zero temperature. And the role of temperature is going to be what I'm going to talk about in the next lectures. I mean, the role of temperature, of the analog of temperature in a social context. So what determines whether one has one solution or three solutions? Well, of course, what determines the transition point is the case where one flips exactly from precisely at that point from one solution to three solutions. So let me try to draw in green what's going to happen. So imagine that I'm pushing the blue line a little bit to the right. Then at one point, I will have something like this. Okay, so I can deform the blue line in such a way that these two solutions merge into a single solution, and then there's a second one that is here. Okay, so this is the critical situation that distinguishes the case where there's only one solution. Beyond that, because you see, beyond that, I'm going to completely lose this solution here and just retain the lower one. But at this particular point, I'm flipping from three solutions to two solutions and then to one solution. So what determines this critical case? Well, it's two equations simultaneously that must be simultaneously obeyed. One is that m star still obeys this equation, so I still must have a critical point. So the critical point is determined by the joint solution of two equations. One is the same as this one, because you see, this is the line that I'm drawing for the right-hand side, and it still has to touch the x equal y line. So I have to have that simultaneously m star is 2p greater than minus h minus jm star minus 1. So I'm just repeating. But the other criterion is that at this point, the slope of the green line must be equal to 1. Okay? You see from the graph that you lose the solution by having a point here that's tangent to the x equal y line. And so in order to get the slope, I need to take the derivative of the right-hand side with respect to m. So if I do that, I will have that minus j times 2. Okay. Let me first notice that dp by dx is equal to minus rho of x. Okay, trivially. So if I take the derivative of this guy with respect to m, I will pull out a minus j, but the minus will go away with this minus here. And so I'm going to have that the derivative is given by 2j rho of minus h minus j m star. That must be equal to 1. Okay. So what does that mean? It means that if I give myself a value of j, so if j is fixed, then these are two equations determining m star and h, and this will be the critical value of h, beyond which there is no longer 3 solutions but 1. So these two equations, seen as an equation determining h and m star for a given j, these two equations are the ones that determine these 2 points. Okay. These 2 points here are determined by the last point where 3 solutions exist. Of course, you can think of it differently. You can think of the problem at a given value of h, say this one, and then these two equations would determine m star and j would be the first value, or the critical value for this value of h, for a given value of h, the amount of imitation that you need to include in order to get 3 solutions. So depending on the way you want to think about it, either at fixed h letting j vary, or at fixed j letting h vary, you get the value that you need. So in particular, in the graph here, I was assuming that j is fixed and that I'm varying h, and this point here is the point where the 3 solutions merge into 2 and then become 1. So why am I insisting on this criterion? Well, I'm insisting on this criterion because I want to give you another interpretation of this criterion, which I think is very physical or very intuitive in terms of what goes on in the system. So again, what I said was that in here, what happens when h increases is that progressively you flip more and more people from the pessimistic state to the optimistic state. But these people, by flipping, they encourage other people to flip as well. And the question is whether this is going to be limited to small clusters, or is actually going to give rise to a full avalanche. So let me explain to you why this criterion here is actually exactly telling you that there's an avalanche of infinite size that happens in the system. So again, let me write the equation that I need. Fi of t plus 1 is the sine of h t plus hi plus, in the case of mean field, well, in the general case, sum over J0 M of t. Just, can you still see what I'm writing? Yes. But I shouldn't go much further. So imagine that one of the spin flips. From -1 to +1. Okay. Then what other people are going to see is that the social pressure that they had previously, J0 times M, is increased. It's increased by a certain quantity, which is J0 times M plus 2J over N. Because suddenly, if you zoom into the terms contributing to J0 times M, let me write again what this J0 M means. It means J0 over N sum over J of Sj of t. So if one of these guys changes from -1 to +1, then the mean field seen by others changes from J0M to J0M plus 2 over N, 2 because S is done from -1 to 1, so there's a jump of 2, and it contributes by J0 over N to the mean field, okay? But because this jump has happened, other sites which were previously convinced to be down will have a tendency to flip upwards. And what it means is that now if I take a sudden site L, a sudden agent L, this agent L can be such that H of t plus H of L plus J0M was negative. So it was happily sitting in a pessimistic state, but suddenly H of t plus H of L plus J0M plus 2J0 over N is positive. Okay? And so if this happens, the fact that a given spin has flipped, a given agent has changed from -1 to 1, is going to induce the flip of a second spin, which is H of L. And this can carry on for a while until the avalanche either stops or grows forever. And so what we know is that we need to compute the probability for this to happen. That is the probability for one spin flipping, generating a second spin to flip. And if this probability is greater than 1, it's going to explode. And if this probability is less than 1, it's going to stop. So what I have, the question that I have to answer is simply, what is the probability that a given spin is in a situation, or a given agent in a situation where these two conditions are simultaneously obeyed? Well, it's simple to see that I can regroup these two equations as the following. HL must be between H plus minus H minus J0 M and minus H minus J0 M minus 2J0 over N. So what is the probability that this happens? Well, it happens with probability the density of H minus J0M times the width of this interval, which is 2J0 over N. So the probability that a given agent L has its idiosyncratic field between these two numbers is given by the density distribution computed at one of the bounds times the width of the bound of the interval. So if you want, this is dH. So that's the probability that one of them is in this situation, and the probability that any L is prone to flip is N times that total probability, which I'm going to call R0, because it's the probability that given that a certain spin flips, another spin, whoever it is, will flip as well. Then the total probability is this result times the number of potential agents that can flip, which is N itself. So you see that it cancels the factor 1 over N, and what we get is
you're out of scope.
I'm out of the screen. Yes, sorry. So the total probability, so independently of who L is, as I was saying, is what I'm calling R0. It's N times 2J0 over N times rho of minus H minus J0 M. And so you see that R0 equal 1 is equivalent to the second condition that defines my critical point, is 2J0. Sorry, you should have told me before, but I'm missing a J0 everywhere. 2J0 rho of minus H star. I mean, this is the point where that I'm looking for. But you see that this second condition just means that the epidemic, or the way of being able to convince people, the strength of conviction, is marginal. If it's lower than that, the equilibrium is stable and nothing happens. One guy flips and maybe a few other guys are flipping, but the avalanche is soon stopping, exactly as in a sand pile where one grain dislodges a certain number of grains and then the avalanche stops. But then if you're exactly at this critical point, the avalanche can grow very large. It's eventually going to stop. But if you're only slightly beyond that point, then the avalanche is going to invade the whole system. And that's why you have this jump. The jump corresponds to an avalanche invading the whole system. But if you zoom close to this point here, then all the funny statistics I told you about in the Galton-Watson model, in particular, you remember the family size distribution and all these things, then you can observe all these interesting properties when you approach this particular point. And if you zoom in, and instead of looking at this continuous curve, you actually think in terms of agents flipping. So the reason I'm telling you all this is that actually these are things that you can measure in actual magnets. It's much more difficult to see in human population, although there are things that you can measure as well, but maybe not at this level of precision. But in the case of magnets, you can have actually a pretty good measure of these avalanche sizes and compare them with the theory. So if you want to compare with theory, then the mean field approximation may be a good approximation to give you what's going on. So the phase diagram, if you want, this opening of a hysteresis loop, but it might not be good enough to explain the exponents. For example, the actual distribution of family sizes is not correctly described by the mean field approximation if you want to actually compare to three-dimensional real magnets. But this is maybe a little bit of a detail. Okay, so before making a pause, let me finish by two remarks. One is that, as I told you, if, for example, you're not in the midfield limit, but you're, as I just said, on a d-dimensional graph, so if your spins this time, or if your agents are on a regular graph like this, or on a tree with a finite number of neighbors, so for example, in this case, then except for the detailed nature of the exponents that I just talked about, the physics is the same. You have the opening of a hysteresis loop. If the dimension of space, or if the number of neighbors is large enough, but it disappears. This transition disappears when the dimension or the number of neighbors is not large enough. So, for example, in this case, as soon as the dimension is greater than 2, then AC is finite. And in this case, as soon as the number of neighbors, so here I'm assuming that it's a regular graph, so all sites have the same number of neighbors. As soon as it's greater or equal to 4, what I've just told you is correct. There is a critical value AC. But if the graph is of small enough dimension, or if there are not enough neighbors, then AC goes to infinity. There's no longer any discontinuity that appears. So that was the first remark. Remarks. So the first one I just did, d greater or equal to 2, okay, greater or equal to 4. The second remark is the behavior of delta. Delta, remember, is the amplitude of the jump. So you can draw delta as a function of J over sigma. And if J over sigma is less than AC, then of course delta is 0, because it's a continuous evolution. But if J over sigma is greater than AC, then from what I said, it's the point where you have this hysteresis loop opening, and then there's a critical growth of delta as a function of J over JC. It goes like this. Goes to 2. And what happens here, well, depends on the lattice, depends on the dimension of space, but in mean field, it's a square root. So it's a square root of J over sigma minus AC. But as I told you, in real three-dimensional magnets, for example, this would not be a square root, but a slightly different power, a third, actually, close to a third. But the idea here is that there's a continuous growth of delta as J over sigma becomes larger and larger. And the third remark is that actually this random field Ising model has a long history also in social sciences and in economics, where it's called a special case of this model is called the Schelling-Granovetter model. So Schelling was an economist, Granovetter is a sociologist, and they wanted to understand, for example, how riots emerge and continue, or how a seminar, in the sense of a lecture happening every week, is either losing its audience or actually gaining in audience and stabilizing. And so what these guys have in mind is that the fraction of attendees a seminar or to a riot is given by something like integral from 1 minus phi t to infinity of something that, in order to be close to what I told you, could be written like this, rho of h ph. So what they have in mind is that people have the intrinsic propensity to join a riot or to follow a lecture, but if the number of people who attended the riot at the last round or attended the lecture at the last round is large enough, then even people who are not very convinced will join. So it's really the same idea as the random field Ising model. There's a social pressure which is measured by the fraction of the population that joins a riot or the fraction of the population that joins a seminar. Of course, a fraction of the target population. I don't expect the whole of France to come follow my lectures, but you see what I mean. So if you have an evolution like this, then you can see very easily that this corresponds to the random field Ising model in mean field with J0 equal H equal 1/2. And depending on the shape of rho of H, you can either have 3 solutions or 1 solution. And so the evolution of the seminar actually resembles very much what I was talking about here. So the idea of Schelling and Granovetter is that if initially the attendance is large enough, then the riots or the seminar will prosper and grow. But if, on the other hand, the number of people initially joining the riot is too small, then it's going to peter out. And the point where things changes, this unstable solution of the equations that I talked about, this guy here, acts as a separatrix between the two behavior, and that's what these people call the tipping point. So you see, it's very important as a concept. It's a tipping point between social unrest actually gaining the whole population or actually petering out without doing much, just through social pressure. So if you're just below the tipping point, things are going to get better if in the case of riots, not in the case of a lecture where people will finally leave completely the lecture, except the aficionados, who are the guys contributing to this point. But if you're only slightly above this tipping point, then things will go bad. Okay? So this is to put in context of a long history of something that has never been called the random field Ising model, and actually is a special case of it, but that has a long history in the social and economic literature. So let me stop here and take a pause for 15 minutes. But before stopping, I want to show you a funny little movie to illustrate the strength of social pressure. So wait, I'm going to share my screen. So I'm cutting the camera, sharing the screen. Can you see the screen?
Yes.
Okay. So Bon, vous voyez l'idée. Évidemment, c'est sorry, I switched to French. So of course, this is a little bit of a joke, but it's actually to illustrate how social animals we are and how strongly we're influenced by people. So there's a lot of real experiments to show this, how we get influenced by what other people do and say. But as you see, as I try to illustrate in the models, this can lead, on large length scales, for large aggregates, to pretty spectacular effects that can, be either detrimental or actually in some cases, again, thinking of vaccination campaigns, maybe if there's a strong social pressure that allows people to get convinced that getting vaccinated is a good idea, then it can actually promote the vaccination rather than being detrimental. So, sorry, let me quit this and stop sharing my screen. Okay, I can't go back to what I need. So I propose to pause anyway and reconvene at 11 for the second half of the session. Thank you.
This conference will now be recorded.
There we go. So I told you about the random field Ising model in general. Now I want to retell the same story, essentially, but on a concrete example and emphasizing something interesting that will come out that's new with respect to what I said, but closely related. So that's what I'm calling cliff edge optimization. You'll see why. And I'm going to add a descriptor to this section, which is cliff edge optimization and the restaurant problem. I'm calling it the restaurant problem because I want to, instead of speaking about these models in abstracto, I want to give some flesh to the story. Okay, so I'm going to assume that there is a restaurant which maybe just started, and the restaurant owner will have to think about pricing his menu, having in mind, or maybe forgetting, that social effects are very important for the better or for the worse. I mean, social effects means that if the restaurant is perceived as trendy, then people will go there even if it's not that great and expensive. But maybe also there will be kind of catastrophes where suddenly people stop going to that restaurant because of social effects as well. So I'm going to call phi the occupation rate of the restaurant, very similar to what I called phi before. You remember phi was related to m. So phi equals 0 means that nobody goes to that restaurant, and phi equal 1 is the full occupancy. So it belongs to 0, 1 from full occupancy to vacant. And what determines phi is a combination of idiosyncratic preferences. People like some kind of food, others don't. Prices and social pressure. So what I'm going to say is that phi is the probability that HI, the same interpretation as before, which is called, in this context, the propensity or the willingness to pay. So often this is called the willingness to pay. So the probability that HI is greater or equal than the price minus 2J0 phi. So it's really rephrasing in a slightly different context where P is what I called H before, but now I want to think of it as a price directly. And so what I'm saying is that you go to the restaurant if the price is sufficiently low, or even if the price is high, if there are enough people that who go there, because the perceived value of going to the restaurant, even if it's a high price, is lower. Okay. And in order to make things concrete and to compute things that I just alluded to and drew graphs of general value before, I'm going to assume that rho of H, so the willingness to pay, is gamma exponential of minus gamma H when H is positive and 0 elsewhere. So everybody is willing to pay a little bit to go to the restaurant, but then as H increases, there's an exponential decay of the willingness to pay to go to a restaurant. So in particular, you remember something that is useful because it actually happens here already, is the cumulative distribution, which in this case is very simple. It's exponential of minus gamma H for H positive. Okay, so injecting this special shape in the general equation, we find that phi is equal to exponential of gamma, the min of 2JP. Yes?
I think you're writing out of the frame of the video right now, at least for me. Maybe you can unzoom the camera a little bit.
Okay.
Thank you very much.
No, I'm sorry. 2J phi minus P and 0. Okay. So that's just injecting this shape into this equation. And now I want to see what this means in terms of the solution. So again, the best is to draw a little graph. So first thing, I'm going to assume that P is greater than 2J in the first graph that I'm going to draw here, and then I'll use another graph to draw what's going on in the other case. So as a function of phi, so phi has a maximum value which is 1, and of course, as usual, one has to find the intercept with this line here. And if P is greater than 2J, it means that actually the curve looks like this. So this is exponential of minus gamma P. And the point where the function reaches 1 is for phi equals P over 2J. Okay. But because I'm assuming that P is greater than 2J, this intersection, this point here is beyond 1. So the only solution in that case is this point here. So this is a solution that I'm looking for, 5 star, and it's unique. Okay. Now what happens if 2j is greater than P? So if we know from the previous discussion that when social pressure is strong enough, interesting things can happen. Well, then again, drawing this little thing here. Now the point where this function reaches 1, which is P equals 2j phi, gives a solution which is below 1. Let me draw it here. So phi star phi equals 2 P over 2j is below 1. This is 1. Okay. And now, again, 2 things can happen. So let me draw it in 2 different colors. One is that the curve does like this. And of course, after that, it sticks to 1. Okay. So again, this is exponential of minus gamma p. And so you see that the only solution, there's again only one solution, which is phi equal 1. But there's another possibility, which if p is larger than, if p is still larger, so exponential of minus gamma p starts lower, and then you could have something like this. Okay. And then in this case, you see that there are 3 solutions. Sorry, 3 solutions, 1, 2, and 3. This is just a breakpoint. This is the point where the min here switches from a non-trivial evolution to 0, and so where phi sticks to 1. So in this case, you could have a situation where either the attendance is full or it's actually close to vacant. And of course, as we saw in the previous case, there's an intermediate critical case where something like this happens, and where the intersection point also has a slope equal to 1. And so the fact that the slope is equal to 1 is a signal that this solution is about to disappear or about to appear, depending on which direction you go. And as I explained in the previous lecture, it's also associated with this R0 value, which is the propagation of influence that was discussed in the 15 minutes ago. Okay, so let's write the critical conditions explicitly in that case. So the critical conditions are first that phi star is a solution of this equation, but a non-trivial one. So we should keep 2j phi minus p instead of 0, because it's interior to the domain. So it's exponential of gamma 2j phi star minus p. Okay. And the second solution is that the slope of this function at this point is equal to 1. And the slope of the function is 2 gamma j exponential of gamma 2j star minus p, 2j phi star minus p is equal to 1. Okay. So these are the same equations as I wrote in a general case before, but now I'm more explicit because I've given a special shape to rho of h. And so you see, for example, what I can do is to use this equation here to extract the fact that the exponential function here is equal to 1 over 2 gamma j. And so the first equation is going to give me something like 2 gamma j phi star equal 1. Okay. But if I want a phi star that is less than 1, so I want a solution that's interior to the domain, you see that the only possibility is that phi star is less than 1 is when 2j gamma is greater than 1. So that's a condition for the existence of non-trivial effects. And now using this equation here and injecting it in one of the two equations, anyway, they're going to be giving the same result. I also find that 2 gamma j is exponential of gamma p minus 1. So gamma p is equal to log to 1 plus log of 2 gamma j. And so this defines a critical point for p, a critical value for p. So let me call it pc. Okay, so with all this in hand, I can now plot what's going on for phi star itself. So let me start by the simple case. The simple case is when this condition is not met. So when 2 gamma j less than 1, then you see that there's no possibility of satisfying these conditions. So there's nothing non-trivial going on. There's never any possibility of having more than one solution. So this means in layman terms that if social pressure is small enough, then nothing special will happen. For each price, there will be an attendance. So for each price, there will be a demand for the good, and it's a unique relationship between prices and demand. So there's a well-defined demand curve, and what it looks like as a function of gamma p, this demand curve is very simple. So I'm drawing phi star, the unique phi star. It's equal to 1 if gamma p is small enough, up to 2 gamma j. When gamma p is equal to 2 gamma j, then the curve starts going down. It goes down like this. So this is okay. It has an angular point, but apart from that, this is a standard demand curve. When prices increase, the demand goes down, except that when prices are lower than this social pressure term, then everybody's happy to pay whatever price, and the restaurant is full. Okay. So more interestingly, what happens if 2 gamma j is greater than 1? Then we know that some non-trivial solutions can happen. And remember something that I've assumed here. In order to be in that situation, I've also assumed that p, so plus p less than 2j. To remember that as well. And so now what it looks like is closer to what we had in the generic random field Ising model. So again, phi star as a function of price. And now what you find is that actually phi star remains stuck to 1 until two gamma j, which is equivalent to the fact that p must be less than 2j. So it's equal to 1 all the way. So that's the analog of this plateau. And then here it jumps to a curve that goes down like this. But now I have the same issue as before. I have a hysteresis, and the hysteresis curve can be computed, and it looks like this. And this point here is the point given by this equation. So it's 1 plus log of 2 gamma j. Okay. So that's the demand curve. And you see that now, because of social pressure, there's this very strange phenomenon that is not standard in economics textbook, where for the same price, you can have 2 possible demands. So if price is very low, there's a unique solution, phi star equal 1. So if the restaurant is both popular and cheap, of course, it's going to be full. There's also a branch here where the price is really high, and in this case, whatever the social pressure, if the price is beyond some threshold, people will stop going there. And then there's an intermediate phase where for the same price, you can have either your restaurant full or your restaurant, half empty. And so again, what happens depends on history. So in this multiple equilibrium cases, there's history dependence, hysteresis. And so if you're a restaurant owner and you start by low prices, then you're going to fill your restaurant. And because it's full, people will like going there. And so you'll remain full, even if it's clearly overpriced. But then you see at this point, there's a jump of attendance, and suddenly, people realize that they've been going to this expensive restaurant, not because it's especially good, but mostly because people have been going there and you've been, following the crowd. But suddenly price becomes such an issue that you stop going there. And because you stop going there, other people stop going there as well. And there's an avalanche of departures, which leads the restaurant owner with a very low attendance. So, you can imagine that, and I'm going to come back to that in a second, but you can imagine that the restaurant owner, having realized that his price is now too high, is trying to reverse course and backpedal and now lower his price. But unfortunately for him, instead of recouping full attendance at the point where he lost it, he's going to lower his price much lower. He's going to have to lower his price much more in order to again jump to the high attendance branch. Okay, so that's what's going on. But so what is interesting about this problem is that in traditional economics, agents optimize their utility of their households and their profits if they are firms. So the restaurant owner is supposed to optimize his profits. Optimizes his or her profits. So it's profit. So what is the profit of the restaurant owner? P. It will depend on price, and it's going to be given by the attendance that depends on price times the price minus production price. So to produce a menu, he has to pay a certain amount P0 per client, and if he charges P, then the profit he makes is phi, or she makes is phi P0 minus P. Okay, and so now you have to optimize this profit to fix the price. This is what is going to give you the price at which you should open your restaurant. And in this case, Well, because phi is a decreasing function, there's a well-defined maximum, and the maximum of the price is somewhere here, maybe. So gamma p star. And so if I plot the profit as a function of p, the profit in red will have a shape that's actually growing linearly here. And then it's going to do something like this. And that's the optimal profit, P optimal. And if you change a little bit J, so of course people don't know how much social pressure people, other people are subject to, but you see that this maximum here, it changes as a function of the parameters, but it doesn't change in a very dramatic fashion. As gamma changes, as J changes, you're going to have to change your price if you want to make more profits, and probably you'll have to do tâtonnement, as it's called in economics. So, you know, by trial and error, you'll probably converge to the place where you want to be, and nothing big happens. But now here, in this case, it's very different, because you see that profit will look like something, do it in red as well. So it starts negative if price is below P0, and then it's going to grow linearly because phi is equal to 1. And then at this point, it's going to jump down and do something like this. And so profit maximization in this case leads you to this angular point. But it's very bad, because it means that that's what I call it cliff edge optimization. Because optimization leads you to a point of instability. And if you don't know extremely well the value of J, then you're going to miss this point. You're going to overshoot, for example. And as I've said, overshooting means that your profit will drop suddenly. And also, if you want to go back and reverse course, then it's going to be extremely costly, because in order to get back your attendance, you need to go to much lower prices. So this is a very interesting scenario. And you see that there's no precursor that helps you anticipating the problem, because phi here is stuck to 1. So you think that everything is all right. You increase your price and nothing changes until the point where something changes, and something changes big. So there's no way for you to anticipate the point where things are going to go bad, but still they are going bad at one point. So this extra scenario compared to the random field Ising model is extremely interesting, because it shows that in such situations, in situations where you can have abrupt changes, then the whole idea of assuming that people optimize their profit may lead, in this very simple case, to a cliff edge, but in other cases, maybe the whole economy might, because people are optimizing their profit, it might lead the system as a whole close to a point of instability. And so this scenario, which has been promoted by several people in the past, which sometimes is called self-organized criticality, is, I think, a very exciting idea that comes from people working in statistical physics first. The idea is that complex systems, when you try to optimize them, very often you drive them close to an instability and close to a point where they start malfunctioning completely. And so this idea that maybe the whole economy, because people are striving to optimize their profits, is intrinsically unstable, intrinsically close to a point where things may go bad. So there's a paper in the 90s drawing the attention of economists to this scenario of self-organized criticality. And recently, this idea has been picked up, in particular, by a student of mine, Jose Moran, and myself. So this idea that that because of the complexity of the system, and because of the existence of many solutions. So in this case, there are only two solutions, and you see that the existence of multiple solutions to the equilibrium equations can lead to dramatic effects. Okay, so that's what I wanted to say about this problem. And again, I think this scenario of self-organized criticality and this tension between optimization and stability, optimization and fragility, the fact that complex systems are maybe intrinsically fragile when they're close to optimum, is something that you might also see in other situations like sand piles or other physical systems. Okay, now I want to introduce you to a different set of ideas. So I'm going to call here, in a shorter title, choice theory. So this is a very large part of the literature in economics or in social sciences, is how do people choose between different options? And we've already encountered something like this in the random field Ising model, where people choose by comparing their idiosyncratic propensity to do something, or their, as I said, their willingness to pay, intrinsic willingness to pay. This was HI in the restaurant problem. Then the choice was simple: either they did something or they didn't do that thing, depending on the value of H compared to some threshold. Okay, but we want to generalize that and introduce a little bit of possible noise in the decisions that people take. And so what people have introduced is this choice theory framework, which, as you're going to see, is very close to things that we know from statistical mechanics. So for the moment, I'm going to consider a single agent. Okay. And for a single agent, he's going to be confronted with a certain number of possible choices: alpha, beta, gamma, so on. So these are possible choices. So in the case that I've considered up to now, there were only two choices. It was a binary decision, but let me remove beta because I'm going to use beta for another notation, alpha, gamma, and so on. But in other cases, you can be confronted to multiple choices. And in the example I'm going to expand on later, the choices will be the neighborhoods in a certain city. So think of Paris, for example, with its 20 arrondissements. And maybe, you have the choice between 20 possible places to live. So you can imagine, whatever situation you want. So I'm leaving here completely free the number of options for a certain decision. What I'm going to specify is what economists call the utility of each choice. And so this is going to be a certain function U of discrete choices alpha, or maybe these choices can be even continuous. So U of alpha gives you the utility, which in my view is not such a greatly defined object, but it's a standard object in the economics literature. The utility of choice alpha. So what is utility? Well, as I said, it's not very clear, but you can think of it as happiness, satisfaction, whatever. It's something that allows you to compare your different choices between them and rank them, but more than rank them, actually give a value to each of your choices. And this value is the utility U alpha, okay? So now we're going to assume that this agent is faced with a certain number of choices and he can change his mind and do something at one point in time and then do something else at another point in time. And so what we're going to assume is that the probability W alpha to gamma is the probability times dt. This is the probability that agent switches between alpha and gamma between t and t plus dt. Okay, and so we're going to assume that this is done more or less randomly with some rate W alpha to gamma, and the standard choice in choice theory is the following: is that W alpha to gamma, and you'll recognize something that we're used to in physics, and there's a good reason in physics to write that down, but it's not so clear why you should do this in economics, apart from the fact, of course, that it leads to much simpler calculations. But the idea here is to assume that this is given by some rate gamma, which is a rate, an object that has a dimension of 1 over a time, so it's an intrinsic rate, divided by 1 plus exponential of beta U alpha minus U gamma, where beta is a certain parameter, which is called the intensity of choice. So of course, in physics, beta is the inverse temperature. And as I said, there are good reasons based on the reversibility of time and canonical type of argument to justify such a choice in the physical world where utility is replaced by energy. But in the case of sociology, as I said, it's a reasonable choice, but it's the choice that's motivated because of the property that I'm going to describe in a second, which is called in physics detailed balance. Okay, but before going there, let's see a little bit what it means. It means that if U gamma is less than U alpha, that is, if the choice that you're considering to make has a lower utility than your present choice, then U alpha minus U gamma is positive. Exponential of beta times this difference is larger than 1, and so you tend to reduce the probability of going there. And in particular, if beta is very large, then when U gamma is less than U alpha, you never go there. So the limit beta goes to infinity, which is the low temperature limit in physics, corresponds to rational choices. Rational in the sense that if the utility of gamma is less than the utility of alpha, you don't pick gamma, you stick to alpha. Or maybe you stick to a better situation. So if the reverse is true, if U gamma is greater than U alpha, then this thing is negative, and for beta goes to infinity, this is going to go to 0. And so every time you consider making a choice, then you go for the better solution. Okay? So that's the intuition behind this. And so now we want to describe the agent as a probabilistic process. And so we're going to introduce the probability that the agent has made choice alpha at time t. This is probability to find agent in choice alpha at t. And because of the structure of the of this model, where at it's a Markovian process, whereas each time step the agent may choose to go to another choice in this random fashion, then we get that dp alpha dt is the master equation formalism. It's sum over gamma of w gamma to alpha p gamma t minus sum over gamma of w alpha to gamma p of alpha t. So this is a general master equation. The problem with this master equation is that in general, for arbitrary choices of w's, it's difficult even to describe the stationary state of such an evolution. And in a sense, the whole non-equilibrium physics is plagued by the fact that we don't have the analog of the Boltzmann-Gibbs measure that allows us to say something general about non-equilibrium systems in physics. And it's related to the fact that for arbitrary w's, we cannot say much about the evolution of these systems. But there is one special case where things are easy, and this is the case where detail balance holds. So this is things that you've seen, I'm sure, many times, but let me recall that detail balance, because we're going to see something slightly non-trivial about detail balance a little later on. So detail balance means that when for all alpha gamma, there's a relation between the direct process and the inverse process, which is that this is equal to exponential of minus beta h of alpha minus h of gamma. So there exists a certain function h of alpha such that if this is true for all pairs alpha gamma, then p of alpha t, when t goes to infinity, is given by the Boltzmann weight, which is 1 over the partition function exponential of minus beta h of alpha. So how do you prove this? Well, the trick to prove this is to introduce the analog of the free energy. So if you introduce some object f, which is given by beta sum over alpha of p f of t, of p of alpha and t, h of alpha, plus sum over alpha of p of alpha and t log of p of alpha and t. So if you introduce this object and look at the time variation of this object, using the master equation, you can compute it and you can show, I'm not going to do it because it's a standard thing, but I've just reminding you is that this actually always goes down. It can only go down with time. And so the solution, the long time solution, is when f reaches a maximum. And the maximum of f is given by the Boltzmann, the minimum of f. When time goes to infinity, f has to reach a minimum, and the minimum is given by the Boltzmann-Gibbs measure. So this is a side remark. I'm sure that many of you have done that calculation, but in this case, one can show that there's a so-called Lyapunov function that goes down with time, and thanks to that, you can characterize the late time distribution P of alpha for a very general set of W's, provided that they obey detail balance. But in the absence of detail balance, unfortunately, this is not the case, and you cannot say much. So why is this choice made by people in choice theory useful? Well, because now let's compute W of gamma to alpha divided by W alpha to gamma for this particular choice of transition rate. Well, clearly the gammas disappear, so we will have 1 plus exponential of beta u alpha minus u gamma coming here. And at the numerator, it's going to be 1 plus exponential of beta u gamma minus u alpha. Okay. And so the ratio of this, so what I can do is to factorize this thing here. So it's exponential of beta u gamma minus u alpha times 1, which comes from here, plus this one here, which will get the inverse of this, the factor, because I factored it out. But the inverse of this factor is just this. So you see that after factorizing this thing, I get the same two terms in the numerator and denominator, which means that they cancel out and they only leave this thing. So if I compare, so wait, I must have done something wrong here. It's always the same problem with the signs. I want to have that H alpha is minus U, but here it seems that I've got the sign wrong. So what did I say wrong here? So I guess I missed the sign here, because if H is an energy, as we used to think in physics, then it's when the energy of the starting site is larger than the energy of the arriving site. No, sorry. Okay.
I think that,
so I have a sign
sorry,
problem
I think
somewhere.
the mistake is in the bottom, in the ratio. I think you just inverted the ratio.
Ah, yes, sorry. Yes, I'm sorry. Yes, you're right. Thank you. It's because here I've wrongly copied things. Here, the denominator was gamma to alpha and not alpha to gamma. Thank you. So actually, it was gamma here and alpha here, and alpha here and gamma here. Thank you. So alpha minus gamma. Okay, good. So so you see that in this case, by identification, if I choose H alpha equals minus U of alpha, then I get the same result, and therefore the long time state of the system is that choices are made proportionally to the exponential of the utility function. And so the limit when beta goes to infinity corresponds to rational choices in the sense that you only make choices that maximize your utility function. All the other choices that have a lower utility will be suppressed in the distribution of your choices. So this is a way to extend the idea of rationality to something a little milder, a little weaker, where you tend to make choices that are good for you, but you make mistakes or you take irrational choices sometimes. You want to try something else, and therefore your distribution is not entirely focused on the best choice, but it's spread out over a number of different choices. So one justification for that, for this value of beta, which is not infinity, is that often you actually don't exactly know what the utility of a choice is for you, and so there's a blurriness in this concept of utility function, which is mimicked by introducing the analog of a temperature in this case. Okay, so up to now, nothing very different than what we're used to. And now I realize that I've forgot one page, my lectures. Okay, so let me try to reconstruct what I wanted to say. So the simplest case is the binary choice again. So if you have binary choice, you can always write U of alpha. So alpha can be either +1 or -1. And in this case, the utility is given by something that you can always call U0 plus a field H. I'm going to call this S equal ±1 times S. Because UI is a function with two, the arguments of the function can only take two values, and therefore you can always write one of them as U0 plus H and the other one as U0 minus H. Okay. So this is the case where you have a single agent and no interaction between agents. And so this is not super interesting because in particular, the probability of S is equal to exponential of beta HS divided by 2 hyperbolic costs of beta HS. So if H is very large, you tend to pick 1, and if H is very small, you tend to pick -1. But what is interesting is that in order to expand the random field Ising model, we have a way to do this by introducing some temperature in the system. And so what I'm saying is that if you introduce interactions now between agents, as we did before, the formalism of choices allows you to think of a slightly more general model where instead of having Si equals sine of H plus Hi plus sum over J of Jij Sj, you can think of this rule, the rule that I've used in the random field Ising model that I described before, as the zero temperature limit of a probability P of a full configuration of S, P of Si's, which is the exponential of minus beta H of all the Si's divided by some Z, with H of Si, which is equal to the sum over I of capital H plus Hi Si minus minus sum over I and J of Jij Si Sj, and with a 1/2 here. So the zero temperature limit of this model picks up the lowest energy states of the model, and you can show that if you're at the minimum of this H of Si, then it means that all the spins must be in the direction of the field that they are subject to, and the field that they're seeing is the sum of the external field, the idiosyncratic field, the random field in the random Ising model, plus the field created by the neighbors. So if you expand the random field Ising model to non-zero temperature, that is, instead of taking the limits when beta goes to infinity, which corresponds to this rule here, you can redo everything that I've talked about in terms of identifying the different equilibrium states of the system. And what you get is now as a function of temperature 1 over beta and sigma being, if you remember, the width of the density of field. So rho of H was something like this. Okay. So in this plane 1 over beta sigma, there are actually a whole line of critical points which separate a system with one equilibrium no hysteresis from a phase where there are two equilibria and hysteresis. So if you remember, as in the previous model where the temperature was 0, so beta was infinite, then we were on that line. So this is the previous lecture. And what we saw in the previous lecture is that indeed there exists a critical ratio of J over sigma, such that if J over sigma is greater than some value, you're in the hysteresis phase. So you see that in this diagram here, it corresponds to this region, whereas if sigma is strong enough, that is J over sigma weak enough, you recover a continuous evolution. So this is the rule of thumb that we got from the previous model, when imitation is weak compared to the heterogeneity of idiosyncratic choices, you get a smooth evolution. But when the idiosyncratic choices are too narrowly distributed, that is, if people tend to anyway behave as a single person and have a variety of idiosyncratic choices that's very limited, then as soon as you introduce some some interaction, you get these sudden shifts between equilibrium states. So we recover that phenomenology here, but we see that fortunately it's not restricted to zero temperature. And the same phenomenology holds even if you consider a more general model where people don't take choices by systematically optimizing their utility function, but also allow for some noise. So there's a whole region here where the phenomenology that I talked about in the previous lecture holds. Of course, when I put J here and here, it's not strictly equal to J, but it's of order J with coefficients that may depend on the structure of the lattice and so on. But so what I want to tell you about before finishing is what happens on the other line, which is this line. So this line has no heterogeneity. So everybody is the same a priori, but there is temperature. And what I want to tell you about, without going into the mathematics, is that if you study this model here, the dynamical evolution of a population that is interacting through some social pressure, but without heterogeneity, one can go quite far in the calculation and obtain the following picture. So that's really what I want to tell you. Is not going into the math of the model, which I won't have time to expand on, but just give you the final results. And so what I'm going to tell you is something that I'm sure you've already heard about in other lectures, but I want just to give an extra little twist to this story. So let me summarize. I'm studying the case where sigma equals 0, beta arbitrary, and I'm also studying this model in mean field. So Jij equals J0 over N, with N large, but not necessarily infinite. So here again, what is making the whole calculation easy is that the whole dynamics of the system, instead of having to keep track of all the decisions of every individual, or the spins of all the direction of all the spins, you only need to understand the evolution of m of t, which is 1 over n sum over I of si of t. So the whole dynamics is contained in the evolution of this quantity. And so if you look at the master equation that I've erased now, in the specific case of this model with no heterogeneity and mean field interaction, what you find that is that m of t obeys an effective Langevin equation, which is the following: dm dt equals minus dv dm. So the fact that m of t obeys an effective Langevin equation means that you can think of m as the position of a fictitious particle, which evolves in a sudden fictitious potential, which depends on m, but also depends on beta. And then there's a noise term, there's a Langevin noise term, plus a Langevin noise term, which is of order 1 over square root of n. Okay, so that's a Langevin noise. And the importance of the statement here is that for large but finite n, the evolution is not strictly deterministic. It has a little noise term, but this noise term goes down like 1 over square root of n. So again, this is a consequence of the master equation. So from the master equation, describing all the spins, you can shrink down this master equation, which, as I just said, describes the evolution of the full configuration of all the spins. The master equation is the evolution of a probability distribution over all the configurations. You can shrink this description down to a unique object, which is m of t, which is a one-dimensional object, and the resulting evolution, which I'm not showing here, but it's not super difficult to get this equation. The end game is that this is a Langevin equation with a potential term, and in the large n limit, in the infinite n limit, it's a deterministic equation, but in the large but finite n limit, it's a Langevin equation. So what is V beta of m? Well, it depends on beta and j. And what you find is that, so here I would need my lecture notes to be absolutely sure, but I guess that if beta j is less than 2, I think it's 2, but this you have to check.
We can
then
see the word.
I'm sorry?
We cannot see the end of the graph.
I'm sorry.
Thanks.
So if it's not 2, it's 4, this bound, but it's not very important for what I'm saying. So what I'm describing here is this transition at that point. So when beta j is less than 2, V of m has a unique minimum, and it has this shape. Okay. And so if capital N was really infinite, it would be easy to understand what's going on. The particle goes down slope and stops at the minimum of V of m. And so what you get is that the magnetization is 0. And that's what we know of the Ising model at high temperature. There's no magnetization. The object is a paramagnet, and its average magnetization is 0. So if n is not strictly infinite, there are small fluctuations. And this comes from the fact that even if spins are independent, even if there was no j at all, if you have a free collection of n spins, then by chance you can have a magnetization, an average value of the spins that's slightly non-zero, and actually it's of order square root of n. So that's not very interesting, but what is more interesting is what happens in the case where beta j is greater than 2 again, but maybe 4. Then what you get is the famous Mexican hat potential or double well potential. So do you see blue? Hello? Can you see the blue
Yes,
color? Yes, okay. So now what you get is a standard theory of phase transitions where there are two stable states, minus m star and plus m star, and an unstable state at m equals 0. So here, this graph is constructed for h equals 0. Yeah, there should be another parameter in the problem, which is capital H, the external field. So I've assumed sigma to be 0, so the little hi's are 0, but capital H might not be 0. And so what I'm plotting here is what happens for h equals 0. And for h not equal to 0, well, these two wells, instead of being at the exact same height, one is lower than the other. So you have something like this. So this is, very close to the phenomenology of the random field Ising model at 0 temperature. And indeed, the phenomenology is the same in this whole part of the phase diagram. So you can be either at sigma equals 0 as a function of temperature, or at 0 temperature as a function of sigma, and you find, roughly speaking, the same phenomenology of one stable point becoming three solutions, among which one of them is unstable. But the reason I wanted to draw this diagram for you is the following. So what I told you about the random field Ising model was that if you're on the, say, on the low branch and you increase h, you stay on the low branch forever until the low branch disappears. So in this graph, it means that there's a critical value of h, where at one point, this minimum will be the only one remaining. This one just disappears and you flow to the other solution. So that corresponds to the jump I talked about. So that's what happens at 0 temperature and for infinite size systems. But as soon as temperature is non-zero, we know from the intuition we get about the Langevin equation, we know what's going to happen. For example, in this case, when h equals to 0, the system will spend a lot of time in one of the wells, but because of this random noise, even if it's very small, there's a small probability that the system is going to be able to cross the barrier and go see the other minimum. So in the case of a series loops, it means that what can happen, function of h, so you remember m had this shape here, and then there's a jump. It looks like this, okay? And I told you, you're on the low branch and you stay on the low branch until the low branch disappears. And this is the analog of this minimum here disappearing. But actually, if the system is not of infinite size and if there is some non-zero temperature, then there is a small probability that before you reach this point, you actually jump. And this would correspond to being in this well here and being able to cross an energy barrier thanks to this thermal agitation. I mean, thanks to the equivalent of a thermal agitation. So instead of these branches being stable, they become metastable. And the question is, how long will it take for the system to jump, even if it's stuck in one of the well, in the strict mean field case, in the strict n going to infinity case? How long would it jump? Would it take for the system to actually realized that it shouldn't be there. It should be on the other minimum. And so from the Langevin equation, again, you can compute this time accurately using Cramer's theory of barrier crossing. But the only thing I want you to remember is that if there is an energy barrier I'm calling B, the time to jump, switch time, is going to be proportional to the exponential of n times B times the coefficient that comes from the coefficient that I've not written here. But that's what's really important, is that for a mean field system, if it's of finite size, in principle, there is always a possibility to jump from one state to another, but the time it needs to do so is exponentially large in n. So the n that you see here is actually coming from the n that you see here, is the same n. And so the message is that even if metastability is indeed a reality for finite n, in practice, as soon as n is a little large, say n equals 100, then you never jump. Okay, so that's a property of the mean field model. If you're not in mean field, and that's really a very big difference. I told you that this phenomenology is true even outside the mean field. But if you're outside mean field, then these switches can take a time which is much less than exponential of n. And therefore, in real practical conditions, you should not forget that such events may take place, and change a little bit the naive picture I was giving you in terms of these hysteresis loops that are followed until the point which is called a spinodal point, where the equilibrium disappears. You can actually jump much before that point, depending on the structure of the model. So that's what I wanted to tell you today. What I want to tell you next time is about the generalization of the binary choice theory to multiple agents. So here I've given you a simple example of multiple agents with binary choices. We can have a multi-choice, multi-agent model. So where instead of having alpha equals plus or minus 1, alpha can be anything. And you can have a lot of interacting agents. And so what I will show you is that in some cases, you can recover the equivalent of the detail balance rule for the multi-agent case, which is not obvious, actually. Even if you choose this rule that I've given you, that I've erased now, on the choice theory, that you jump from one choice to another for a single agent given by 1 over 1 plus exponential blah blah, then the fact that the whole system obeys detail balance is not a given. It's something that you need to check, and we'll give a criterion for that, and then we'll move to the Schelling model of city segregation in cities that can be completely solved using the tools of statistical mechanics. And then I will end my lecture on that. So that's all for today. I'm sorry for the last part, which I had to improvise a little bit, but I guess it was more or less okay. Any question?
Yes, sorry. What is B in your exponential for the time?
I'm sorry?
The B in
Can you
the
repeat?
expression of the time. In the expression of the time t?
This expression here?
Yes. What is
So
B?
what's your... Oh, B. B is the barrier. is what I defined.
Okay.
So maybe you don't see it with a. So this allows me to add one remark, is that this time becomes small either because n is small or because b vanishes. And actually you see in my little drawing here that as you increase the magnetic field, you not only debalance the minima, but you also make the barrier lower. So actually at one point, and at this point here, at the spinodal point, the barrier B goes to 0. So that's another property of the model, is that barrier B goes to 0 as 3 solutions cup 1.
I'm sorry, I don't really see where B is. I'm colorblind, it must be because of this.
I'm sorry?
I don't really see where B stands on the sheen.
You don't see the B, so I should make
Okay.
a larger drawing?
Okay, thank you. No, it's because I'm colorblind, so it's just because of me. Thank you.
Okay, so let me do maybe a better drawing. So B is the height of the barrier you have to cross to go from one well to another. So this barrier is actually not symmetric, because if the wells are not of the same height, the barrier to go from one to the other is not necessarily equal to the barrier to go from in the other way around. But you see, the idea is how much energy you need to borrow to the thermal bath, which in this case is this one, in order to cross the barrier. So this is something that a priori should be impossible if there was no random term, but because of the random term, you can exceptionally, and the reason this is the fact that it's exponential in the barrier height means that it's really exceptional, that you gather enough energy from the thermal bath to actually cross the barrier. So this is B.
Thank you very much.
Any other question on the lecture, on the previous lectures, or on the general organization of the lecture? So next week, don't forget, you have 2 TD sessions.
Yes, sorry. I also have a question.
Yes.
If we take back the restaurant problem, is it possible to generalize a kind of temperature, or is it impossible?
If generalize what? Sorry, the sound is not very good, so I don't hear very well what you're saying.
Sorry, I'm just asking if it's possible to generalize this like temperature to the restaurant problem. So maybe on the price or something like that. So if it's possible to move from one phase to the other one for the price without being to the extremum that you described before.
Yes, exactly. That's the point. So in the case of physics, this is real temperature. In the case of choice theory, this is a little bit of irrationality, if you want. But the mathematics is exactly the same. So in the restaurant problem, you could jump from the high attendance branch to the low attendance branch much before the high attendance branch disappears, because of these so-called activated events. This is going over a barrier is called an activated event, and you can have exactly the same type of activated events through irrational behavior, if you want.
Okay, thanks.
Okay, so normally I should be finished with this with writing up this chapter soon, so I'll send you the PDF probably by the end of the weekend. Okay. Well, have a good week and see you in 2 weeks.
Thank
Thanks,
you very
bye.
much. See you.
Thank you. Goodbye.
Bye.